So before starting, let me briefly introduce today's speaker. Today's speaker is Junichiro Kawamura from IBS, and he received a PhD from Waseda University at 2017. And after that, he experienced the postdoc in University of Tokyo and CAU University and Ohio State University. So from 2020, he has been in IBS. Today, he's going to talk about the complete vector-like post family and the new U1 prime for muon anomalies. So Junichiro, please start your presentation.
Okay, thank you for the detailed introduction. So first of all, thank you for inviting me to giving a talk seminar, but unfortunately I cannot visit there in person. But in near future, I'd like to visit there. So anyway, today I'm going to talk about how we can explain the relation to anomalies in muon physics. And this talk is based on these 3 papers. So there are some more details about these works, and in collaboration with Stuart Levy and Andreas Strautner. Okay, so I'm giving a talk along this outline. First, I introduce some new anomalies, and then I introduced our model with vector U1 prime. And then I discuss one unique signal from this kind of model with the prime and the vector leptons. And then I summarize in the end. Okay, so let me start from introducing the anomalies in the MNG-2. So you may know that the new result is announced in this April, and a new result is still consistent with the previous result given by the BNR. And there's still large discrepancy from the standard model prediction, and now it's about 4.2 sigma away. And to explain the size of the anomaly, we should actually need the elliptic size corrections. So this is pretty large for new physics. And also, but to be fair, I should mention about the lattice result itself is actually consistent with more consistent with the experimental values around here. So the tension will be more smaller. But we don't know which is more correct, experimental determination or the lattice calculation is correct. And so in this talk, we take this tension more seriously as an evidence of new physics. So we try to explain this anomaly. And another interesting anomaly found in the B physics. So here I take the RK. RK is roughly speaking, it's the ratio of the branching fraction or the decay width of the B to K mimi over the B to K EE. So for instance, the standard model had this kind of process, or we also had the box diagram. But anyway, so the standard model predicts that this RK is about 1. So which means that this ratio is at 1, and then this is a flavor universal. So in the standard model, this is predicted with the lepton universal and no lepton non-universality. However, the recent experimental result given by the LHCb is actually not a value around 1, but its value is measured at 0.846, which is below the 1. And counting these error bars, then we have the now 3.1 sigma discrepancy. And then please remember that this value is below some prediction of the standard model value. And we rely on these observables because of this is some clean observable because of some cancellation in this ratio structure. And the same we think this observable is more reliable than others, which I discuss in the next slide. Okay, so the more interesting feature about this B2S mimi anomaly is that we have more anomalies in the other observables. So as I said, there's a lepton non-universality is observed in the RK, and we also have some anomalies in the branching ratio of the B to phi mimi or the B to K mimi decays. So these are the branching fractions depending on the Q square, which is invariant mass of the dilepton system. And so here, these colored regions in these figures are the standard predictions, whereas the data is given by these black dots. So now we see that the standard predictions, the experimental data is below the standard predictions in these observables. And also we have some discrepancies in the angular observables. So I don't introduce these observables because this is a bit complicated, but there's also some 3.3 sigma discrepancy in these angular observables. And so now, as I said, there are some discrepancy in these branching corrections, and these various experimental values are below the standard predictions in these observables. So also their discrepancies are still about 3 sigma or so at most, and some of them are just 2 or 1 sigma. But the interesting fact is that these discrepancies seems to point the same direction. These are all below the standard prediction. So if we combine these discrepancies at once, then we could get a more larger discrepancy. So there are many groups try to do that, and it's more easily to analyze this kind of thing by introducing these 4 Fermi interactions involving the strange and the bottom quark and the muons. And these are the operators irrelevant to this BTS minimum decay. And so this is a heuristically introduced ones. But this O9 operator is for the left vector current for the strange and the bottom quarks, but it's vector current for the muons. But for this O10 operator, this is for left vector current for the strange and bottom quark, but this is the actual vector current for the muons. And the primed operator is for the right vector currents for the quark sector, but the same for the lepton sector. Okay, so this is a definition, but we know that the anomaly is more easily explained if we consider the new physics contribution to the O9 and O10, which is a left current vector interaction for the quark sector. So here, there is a global fit of the C9 and the C10 new physics contributions, and I borrowed the result from this paper. So that this includes the latest result from the HCB in 2021. And so that this is a plot on the new physics contribution to the C9 and the C10. These are the Wilson coefficients for these operators. And so that this is the new physics contribution, so the standard prediction that here, but the experimentally favored value is around here. And if we compare this point and this point, then now the chi-square difference is about more than 6 sigma. So, and also, even if we only introduce 1 operator of the C9, if the C9 value is about -0.8, this new physics model can explain the experimental result about by 5.7 sigma improvement from the standard prediction. So this looks like evidence of the new physics. Also, we need a more careful check in the future, but this look nice to start consider some new physics model building from this evidence.
Junichiro, so this C9 fit is the single parameter fit in this result that show this value, right? So if you have a two parameter fit, then you have a C9 and C10, both can be non-zero, right?
Yeah, both can be non-zero. Yes.
Okay.
And in this case, for instance, typically the C10 is about a smaller value compared with C9. In this case, you see that it's about -0.7 or so, and the C10 is about 0.2 or 3 or something like that.
Yeah, but as I remember, if you set C10 equal to 0, and then you can make C9 only C9 free, then you might have this kind of result. And then if you combine C9 and C10, I mean, you can make these two parameters vary. You can allow for a non-zero value also for C10.
Yes, of course. Yeah, we can allow any non-zero values in these operators, and also some related to the operators like O9, O7, or something like this.
Because the C9, C10 only, they are different only in the muon current. So if muon is vector-like or chiral, we cannot say much about that, as I remember. So
there's also actually there are various ways to fit the parameters. Like we can consider that the C9 equal minus C10, like a left current in the muon sector. That's also possible. And actually there are too many possibilities. So we usually restrict the parameter space to 1-dimensional or 2-dimensional. Yeah,
but it seems that what you are saying from this plot is that the vector-like C9 only is a vector-like muon coupling might be, I don't know, more favored. somehow?
Yeah, I think
According to
this
the
is
current.
most favored scenario among the one dimension. And yet it's not sure. So recently there's some anomaly, some discrepancy in the BST mu. And this favors actually no 0 C10 value. So yeah, it depends, but it's this value improvement is actually the similar about 6 sigma.
I see. Okay.
So we are not sure which is most preferred. Yeah, it looks like some new physics contribution enters in somewhere in this parameter space. Yeah.
Okay.
So
thank you.
Please ask me. Feel free to ask a question. Any kind of questions are welcome. Okay, so let me proceed to introduce our model. So our question, it's very nice if we can explain that these anomalies simultaneously in anomalies in BTSB mu and the muon G- simultaneously. So this is our attempt in our model. So we shall consider the vector-like UN prime model. So let me discuss about this. So our idea is pretty simple. So for the muon G-2, we introduce the ion prime symmetry and the vector-like leptons. Then we have this kind of diagram with vector-like lepton and Z prime. And this kind of diagram would induce the new physics contribution to the delta A mu. And by introducing the vector quarks, we may get some coupling with the Z prime to the sum of their fermions. And then this 3-level process will induce the BTS mu processes. And actually, this idea itself is not so new. There are some models that have been introduced in previously. So for instance, the U1 L mu minus delta plus vector lepton quarks proposed in this paper. Maybe this is the first time. And also the U1 prime symmetry can be identified as 3 minus 4 symmetry, is introducing the fourth family vector lepton. And only the third generation, the fourth generation carries the U1 prime charge. Well, there are similar models proposed in these papers. And so, but this is a general picture about how we can explain the G-2 and the BTS mu anomalies simultaneously. But our model is a bit different from them. So the difference, so we again also introduced the vector-like fourth family and the ion prime. But the difference is that only that this vector-like family carries a ion prime charge. And any of the standard particles is charged under the U1 prime symmetry. So then now you see that I only show the new physics particles, but we also have the standard particles on top of them. And the charges are given by here. And we also introduce the scalar fields to violate the U1 prime. So in this way, of course, there's no Z prime coupling to the sum of the fermions in the gauge basis. But however, after the symmetry breaking of the U1 prime, there's a mixing is induced. And then we get some coupling with the standard to the Z prime. And in this way, we can get some Z prime to standard couplings will induce the new physics contribution to the muon anomalies. And the good feature of this kind of model is that unwanted effects can be evaded because of our new coupling with the gauge basis, and we get coupling to the standard model only in the mass basis. So by controlling the unitary mixings between the fermion sector, we can control the Z prime coupling to the new physics, unlike the other models like chiral U1 models or L mu minus delta or 3 minus 4 symmetries. Okay, so it's a bit complicated, but let me show you some details of our model to see what happens explicitly. So here are the Yukawa couplings for the charged leptons, and after the symmetry breaking, we get this shape of the Yukawa coupling mass matrix. So here I omit some of the particles by just included all the 3 generations are included in this E bar and the E air. So this is a 3 by 3 matrix in the chiral Yukawa matrix. And the important point here is that there's a mixing induced by the wave of the large phi, which breaks the U1 prime. So of course, after the diagonalization, we should get some mixing between this chiral family and the vector-like family. And so I note that this similar structure is hold for the quark sector and neutrino sector, but I only show the charge lepton sector because it's too much complicated.
So, excuse me, is there a chiral symmetry in the vector-like fermions?
Chiral symmetry.
In for instance, do you have a 3-level vector-like masses?
Yes, we have. So there's no chiral symmetry this kind. So we have the, so yeah, we write in this way, but actually this can be just simply replaced by the mass term. This may be a simpler way to express the model, but this way we may just could be explained why this is at the same order as the level of the pi.
But here there is no protection.
Yeah, no protection
of large vector-like mass.
Yeah.
So just you set the three-level vector-like mass is to 0 and induce them by this. Okay.
Yeah. So yeah, of course, if we consider this coupling, there can be find some chiral symmetry before the symmetry breaking. But yeah, basically we just consider the vector-like masses for these extra generations. Okay, so we have this mass matrix, and then so we should diagonalize this, and then we get this masses diagonalized. So here the Z prime coupling, which is the most important for the phenomenology. So the important thing is that this is a coupling matrix in the gauge basis, and we see that there's no coupling, 0 entries for the sum of the sector, but non-zero charges in the vector sector. So there's no coupling, but after multiplying these unitary matrices to go the mass basis, then we get the Z prime coupling to the sum of their families. Okay, so this is a more explicit picture how to get the Z prime to the sum of their particles in this model. Okay, so but we should pay attention to the flavor variations, because if we have the in physics contribution to the muon minus 2 by this diagram, if we replace this vertex to the muons to just the E or tau, then we get the flavor violating process like the mu to E gamma or the tau to mu gamma. So, and also we could have this, for instance, the tau to 3 mu decays, which is also another important flavor violating process. And similarly, we may have the quark flavor variation. So if we have the coupling with the Z prime to BS and the mu mu, sorry, mu mu is not flavor violating, but anyway, we have the vertex of the B strange and the Z prime, and then so this vertex itself induces the BS by mixing in this process by Z prime exchanging, so this BS by mixing induced by this Z prime exchanging is unavoidable. So we always have the new physics contribution to BS by mixing, and similarly we could have the V sub D by mixing or the KK by mixing. So we should pay attention to them. And another non-trivial feature is that the CK matrix. So now we have the 5x5 CK matrix because we introduced both singlet and the doublet new vector quarks. So that's the mixing. And the important feature is that we also have the singlet vector quarks. So if it mixes with other families, then there's a non-zero entry here. So this means that the 5x5 this CK matrix is not unitary in general. But however, we found that this model predicts unitarity for this 3x3 matrix for the CKM, for the standard generations. And so now if we calculate, sorry, the star is missing here. Sorry, the dagger is missing here. But so if we consider the unitarity of the 3x3 matrix, then we get actually the almost diagonal structure, and the additional new physics contribution is suppressed by here. The largest contributions may come from the mixing with top quark because of the heavy top quark mass, and its size is expected to be by this size. Here, the epsilon TR is a mixing between the top quark and the vector quark, and it's also suppressed by the top quark mass over the vector quark. So this size is estimated as a 10 to the -6 or so if the mixing between the top quark and the vector quark is 0.01. So I note that the mixing between the top quark and the vector quark is not so preferred to explain the anomalies. So we can naively we can forbid such a coupling. But in such a case, then there's no new physics contribution to the unitarity variation of the CKM. But it will be interesting because we, in principle, have the non-unitarity in this kind of model, and we could explain that. So recently, we have some non-unitarity in the CK matrix in some experiments. So this kind of model could explain the anomaly, such a non-unitarity of the CK matrix in principle. But in this talk, we found that in most parameter space, the CKM is actually almost unitary, as far as the missing is suppressed at 0.01 or so. This is not so severe constraint. Okay, so we try to find points that can explain the anomaly simultaneously without violate the flavor physics, not much. Then we did actually the chi-square analysis, but I don't show you some details, but we did some chi-square analysis with many parameters and many observables. And so we found some good points around like these. So at these points, we see that the muon Gimana is explained, which is very close to the experimental value, like about the 2.5 times 10 to minus 9. So this is some old value, but its value is still similar. And also the C9 and the C10 value can be at these sizes preferred from the global analysis of the C9 and the C10 fit. So basically we can find the points that can explain the anomaly simultaneously. And also we have checked that these flavor violating processes are below the experimental values. For instance, the PT gamma is about 10 to minus 14, and the other flavor violating processes involving the taus are much smaller than the experimental constraints. And also we have studied the Coco flavor variations like B sub D, B sub D by mixing, or the B sub S, B sub S by mixing. So also there's actually the new physics contributions, but these are still small compared with the uncertainties. So these are basically consistent with the standard predictions, not much new physics contribution to these quantities. Okay, so now we showed that we can explain the anomalies nicely. So we are interested in how to find the new physics, some evidence of new physics in some observables. So let me discuss.
So what is chi?
Sorry, chi is so we define the chi-square analysis in a usual way, like
I mean the m chi. Sorry, m chi.
M chi.
M chi mass.
Sorry, yeah. Okay, I did not define the chi. Chi. Chi.
Is it neutral or what is that? Is that dark matter or?
No. Sorry, this is some scalar particles. So we introduced the two scalar particles, and so actually so before studying this explicitly, I considered the possibility that this new scalar field could explain some of these anomalies, but actually I found that there's no such contribution. And so sorry, this would be not so important. But chi is just a neutral scalar field.
So there are, in this case, there are two vector-like fermions. So E1 and E2, I think, in the basis of mass eigenstates. And so here the E2 is kind of decoupled, or you are keeping?
No, actually, no. So I will show you that later. And so actually, this should be light.
I see.
So yeah, in some sense, yeah.
So E2 is lighter than E1, or they are comparable?
No, E1 is lighter, but comparable. So I can show you the figure later.
So here you have some chirality flipping enhancement in the G-2?
Yeah, right.
Okay, I see. Thank you.
May I ask about the chi-squared analysis? In your chi-squared analysis, you chose degree of freedom is 33.
No, we just counted the DOF is just the number of observables minus a number of parameters. So I don't remember the exact number, but roughly speaking, there are 80 observables in the chi-square analysis, and we also have about 50 parameters.
So I see. Number of the parameter. Okay.
Yeah, number of observables minus number of parameters. So like many so
parameters.
yes, you can see actually there's too many parameters here. And so even in charged matrix, charged Yukawa matrix, we have this 3x3 matrix and Yukawa matrix for between the scalar families and the vector families. And here you can copy here. And we have the same matrix for the quarks and the neutrinos. So actually, there are so many parameters, over about 50.
Thank you.
So here we did some very general analysis, but if we don't want to consider the flavor variations by imposing some correct certain symmetry, we could forbid some unwanted couplings, I guess. But we don't do that here. We just do some general analysis without doing such a assumption. Yeah, so we have so many parameters, and we studied actually the bunch of parameters, including the electrical precision also, and this lepton collaboration, and so on. So like all the CKM matrix are fitted, or so that we have so many parameters. Yeah, but I only show the most important observables because it's too long list of the observables.
Junichiro, I have an elementary question for the setup. So you have two scalars, large phi and small phi.
Yeah.
And it looks small phi doesn't play an important role. Is it correct? Why?
Yeah, no. Yeah, these don't play any important role actually.
So, but it's necessary, or I don't know why you need to introduce small phi. Large phi.
No, I don't think so. I think we can just replace this by the mass matrix. Yeah, I agree.
Okay, there's no specific reason.
Yeah, but yeah, the number of parameters are different even if we replace these to just the mass parameters. So just this is just a kind of parameterization.
The small phi is real now.
Yes. Yeah. We assume this is real, but this capital phi is of course complex.
Okay. Thank you.
Okay. So, do you have any comments or questions? So, okay. So great. So let me continue. So here the lepton writing observables. So now, actually we found so many points that can explain the anomalies simultaneously. So here is a result of the chi-square analysis, and actually the both lead points is actually pretty well explained the anomalies simultaneously, and no confliction with the other observables. But the green dots is sometimes cannot explain the muon G-2 or BTS mu decays, or some discrepancies found in the other observables. So basically, you can see only the lead points. And there are enough number of the lead points up here to see some behavior of the prediction of this model. So we see that the x-axis is the branching fraction of the mu2e gamma, while the y-axis is the mu2e. And so now the current experimental band is here. So we see that the mu2e gamma can be as large as the experimental band. On the other hand, this value of the mu2e is very much suppressed, like here the T2-20 or so. So in this model, the prediction from the d prime decay is that just the mu2e gamma is very large, but the mu2e is suppressed. And the right panel shows the tau decays, the x-axis the tau 2 mu gamma, and the y-axis the tau 3 mu. Instead, in contrast to the muon decays, for the tau decays, this can be comparable. I mean, these values are close to the experimental bands on the tau prevalent in the tau decays. And actually, the tau 2-3 mu is slightly larger than the tau 2 mu gamma, so this may be a good place to find our model. So also, you see that our prediction is not so sharp, but we still have some specific pattern of the variability process. So for instance, if we only observe the mu2e in future experiments, then this model can be excluded or something like this. So there's some mild prediction to the pattern of the lepton variation in this process, in this model. Okay, so this is from the tau lepton flavor variations, but we also studied the meso mixing and other flavor variations.
So before going to the quark sector, let me ask about, have you checked the electron G-2 also in this model?
Yeah, we actually tried to explain that we found that it's impossible, as far as I know. So yeah, so
so you have two vector-like fermions.
Yes.
And then I think that the problem of mu-G-2 is if you couple same vector-like lepton to muon and electron at the same time. So is it possible to couple one vector-like lepton to muon, another vector-like lepton to electron, and mixing between the two vector-like leptons might be small somehow? They might have a chance to suppress mu2 gamma.
Yeah, we tried to that,
but
actually we couldn't. We failed.
I see.
So yeah, the naive reason is that to get the chiral enhancement, we need some non-zero entries at here, which means that there's a mixing between these two states. Then, which means that it's, naively speaking, it's difficult to decouple from one to one.
I see.
I mean, yeah.
Okay.
If we can find, so after the mixing, I mean, that's mix the state, for the mixing state, if we decouple them to the muon and electron couplings, then it's possible. But I think it's at least we couldn't find such a point.
I see. Okay.
Yeah, so I think it's very difficult to explain the both anomalies simultaneously.
Okay.
Yeah, so that's another reason why we study this full analysis. In principle, we could explain the both delta AE and the delta ME simultaneously, but yeah, we failed that, unfortunately.
I see. Maybe you need another pair of vector.
Yeah, of course. Then yeah, we could do that.
Fourth, it's not fourth, maybe fifth.
Yeah, maybe we can introduce more.
I see. I see the reason. I see.
But then I think it's more trivial that we can explain the both anomalies if we prepare the both independent sectors.
It's increasing the number of particles.
Yeah. So we didn't do that. So at least in this case, I think we cannot explain that. Okay, so let me go to the quark sector. So here is scattering plots on the delta MD and the delta MS, the mass difference of the BS base bar and the BD bar. And so we see that this red point and the cross is error bar of the sum of the prediction with assuming the unitarity CKM. And we see that our prediction is consistent with this sum of the prediction with the unitarity CKM. So actually, the new physics contribution can be very much suppressed. So our model is basically consistent with the standard model prediction, and it will be hard to be. But in near future, if we have the more precise measurement or the calculation of this BB mixings, then we could get some. We have some resolution to this new physics contribution. But basically, it's still consistent with the standard model. And so there we have studied the flavor variations. So let me turn to some masses of the new physics, new particles. And maybe, of course, the Z prime mass is the most important parameter, maybe. So here is the scattering plots on the Z prime mass and the G prime gauge coupling constant plane. And if we impose a condition that the G prime should be perturbative up to the grand unification scale, then actually the 0.35 is the upper bound on the G prime gauge coupling constant. And so in this case, actually the upper bound that can explain the anomalies. So that we see that the G prime should be lighter than 800 GeV if the G prime coupling is about 0.35, but if it's smaller, the limit is even tighter. So anyway, we have some upper bounds to explain actually the muon G- to the G prime coupling should be G prime should be very light. Okay, so this may be the strong prediction. And also another prediction is coming from the vector lepton. So to explain the muon G-2 and the analytical analysis, we found that there's some region that can explain the muon minus 2. Only inside these curves we can explain the muon minus 2, and we only found actually we found the points only inside these curves. So now we see that, for instance, the Z prime is about 500 GeV. The vector lepton should be lighter than should be lighter than 1.4 TeV around here. So, but if the Z prime is even heavier, then the vector lepton should be as light as 500 GeV also. So there's a strong upper bounds to explain the anomalies in our model. So yeah, there's a strong constraint. And so in the next section, I will discuss about how to find these light particles. So I present one possibility to find that. And so let me summarize my talk so far. So we consider the model with the Z prime and the vector lepton and the quarks, and the muon minus 2 can be explained in this diagram, and the typical size of the muon minus 2 discrepancy can be explained if the Z prime mass is about 500 GeV, and the coupling to the muon and the vector leptons are of the 0.9 or so. And of course, this is coming from the chiral flip effect. So here's the left current interaction and the right current interaction. And also the BTS anomaly can be explained simultaneously by this 3-level contribution if the Z prime mass is again the 500 GeV and the coupling is a disorder. Okay, so, and also I think even in this custom model with Z prime and the vector leptons, not to restrict to our model, if we have these Z prime masses and the vector leptons, then we can explain this anomaly simultaneously. So then next I shall discuss about how we could find these new particles at LHC. So do you have any questions so far? So if no, okay.
Here, let me ask a question on the muon coupling to G prime. So here you said the vector-like lepton G prime couples only to the vector-like leptons at the 3 level without mixing, right?
Yeah, without mixing. Yeah, no coupling even to muons.
The muon.
I mean, yeah, without mixing, no coupling. But actually, there's a large mixing, actually almost maximal mixing between the muon and the vector state.
Muon and vector-like, I see. So is that consistent with the electroweak precision?
Yeah, it's still this. For instance, the muon decay is not so changed. Yeah, muon is coupling to the actually we can hide that from the electric precision.
And also, for instance, delta rho.
Actually we didn't calculate that. Yeah, but it can be suppressed, and in my feeling, I think it's safe, still safe. Yeah, actually the limit is not so tight yet.
And then concerning the quark sector, so G prime couples to bottom and strange at the same time.
Yeah.
So in this case, you also have a fourth vector-like quark, right? I mean, fourth generation. I mean, vector-like quark couples to. Does it couples to a mixes? Does it exist with the third generation only? This.
No. So let me show you some benchmark point. So these are the full data of the mass matrices after the fitting. So you see, this is the up quark sector, and this is the up quark mass matrix. And so so there are some non-zero entries up here, which means that the vector-like quarks are mixed with all the generations. So in this case, actually, it's strong coupled to the second generation. So the mixing between the second generation can be large.
It's a charm or bottom.
Yeah, so actually this is for SU2L doublet sector, doublet quarks in this column. So these are the same entries, and which means that both strange coupling and charm-core coupling is, I mean, sizable, not sizable, but yeah, because of the, the vector quarks actually can be very heavy, like a 3 TeV or heavier. So even though this is a 200 GeV, this can be suppressed in some sense.
Okay.
Yeah. Okay, so let me proceed. So next I'd like to propose a possibility to have the very high multiplicity muon signals from the d-primed vector leptons at LHC. And before going that, I think you may concern about the d-prime such, because we know that if the d-prime decays in the same way as the d-boson, the limit is about 5 TeV or so. This is much stronger than our preferred masses of the 500 GeV of the d-prime mass. So we should care about that. But interestingly, to explain the muon anomalies and also the BS by mixing, actually the favored value of the coupling is given by here again. So the d-prime mass, if the d-prime mass is the 500 GeV, and also to explain the muon J-2, the muon coupling should be large in general. So in this case, actually the preferred value of the coupling to the quarks is generally very small, like a 10⁻³ or 4. So this is a very small coupling. So we can consider the parameter space that the z prime only weakly couples to the quark sector. So this is enough to explain the anomalies with these parameters. So in this way, the production rate of the z prime can be very suppressed, and then we can find the parameter space that the fiduciary cross section is smaller than 1 femtobarn. And we actually found that most points are below the experimental boundary. Also, in some cases, because of some sizable coupling to the bottommost range quark, the production can be large. But at many points, we can find that these are still below the experimental sensitivity. And even below this line, the naively we expect that these points are still not excluded by the high LHC projection. Okay, so some parameter space could be excluded by the d-prime search, but the still significant points parameter space cannot be proved by the d-prime search. So we need other ways to search for our model. And I remind you that we also have the light vector leptons. This can be a good target at LHC. So we discuss about that. So in this case, let me consider about a vector lepton pair production like this. And sorry, this is a bit messy, but let's consider the vector lepton production, and the vector lepton will decay to d prime because these are strongly coupled. So the dominant decay modes may be the d prime, and the d prime will decay to dimuons. So in the final state, we may have at most 6 muons in the final state. So even if the d prime may also couple the neutrinos because it's through its left current interactions, d prime will decay to the neutrinos. Even in such a case, we still have the 4 muons in the final state. So here 1, 2, 3, and 4 muons. Or even if we consider the vector neutrino production instead of the charged vector neutrino, charged vector lepton, we still have the 4 muons in the final state. So this kind of process from in general, the vector-like lepton pair production will induce the more than 4 muon signals in the final state. And this should be a very nice signal at the C because we know that these high multiplicity lepton signals are very rare at the LHC. And so in the following analysis, for simplicity, we assume the following assumptions. The one is we consider the vector lepton is almost a singlet or doublet, and we don't consider the mixed case. So in this case, the production cross section is given by here. And so you know that because of the doublet has both vector neutrino and the lepton, charged leptons, so the production cross section is larger. While the singlet case has a smaller production cross section like this. And for the doublet case, we assume that the charged vector lepton has the same mass as the neutral vector lepton in the doublet case. Okay, so this is one assumption. And the more important assumption here is that the z prime only decays to the muon or neutrino, but not to quarks. So as I said, the Z prime coupling to the quark sector should be very much suppressed to evade the strong constraints from the Z prime such. So we assume that we can neglect the Z prime decays the quarks. So in this case, the Z prime would decay only to the muon or neutrinos. And then, so the branching fraction of the Z prime to mu is given by here. And a more trivial assumption here is that the left current and the right current interaction is the same, which corresponds to the case that the C9 only or C10 only scenarios. So in this case, the branching fraction is given by 2/3. So about 70% of the Z prime goes to the dimuons, but the other 1/3 goes to the dineutrinos. Okay, so this is our assumption. But I think even if we don't require these assumptions, the result will be very similar because the BTSM anomalies still prefer the large C9 value. So as far as this is true, then this value is not so different from this value. And also the cross section is in between these two lines if they are mixed. Okay, and what we did was recasting the atlas analysis search for the high multiplicity lepton final states. And there are more signal regions, but most relevant one are these 3 signal regions. So the first two signal regions, they just require there should be more than 4 leptons, and there should be there can be tau but not the bottom quark, and also the boson is vectored, which means that any invariant mass of the opposite sign same favor charged lepton pair should not be close to the mass of the Z boson. If it's so this is the Z boson vector, and on top of them, these topological requirements, they also require that the M effective should be larger than the 600 GB in the loose region, and also the 1250 GB for the tight region. Okay, so here the M effective defines the missing T plus the PT of the lepton and the jets. And so this is the signal region for the 4 lepton signal regions. And also they study the case of the 5 lepton signal regions, which is just requiring there should be more than 5 leptons. And that's it, no further cuts are required because this is already suppress the standard backgrounds. And here is the experimental result. So now we see that the experimental data gives that there are 11 points in the loose region and one event in the tight region, and there are 21 events in the 5 lepton signal regions. Plus the standard predictions are given by here. So unfortunately, there's no strong evidence for any physics. However, we have some excess in this 5 lepton signal regions. Also, this is just a 1.9 sigma. So this is not so significant, and this is not enough to construct a model to explain this. But as you know, so we already have a model, and as I said, there can be the 6 muon signals in our model, so we could explain this excess. And this would be an interesting question, whether we can explain this excess or not. So I shall discuss about this in the end of this talk.
Excuse me. So what is S95?
Sorry, this is a 95% confidence level upper bound on the signal event. So if the new physics contribution is that predicts the 10 events in this signal region, then that's excluded at the 95%. Yeah, confidence level.
Okay, thank you.
You also put the shield rapidity cut from the detector, not only
shield rapidity for right. Yeah, I don't like maybe like some user cut requirement respecting the atlas detector, like eta should be smaller than 2.5 or 7. Yeah, depending on the lepton flavor. Yeah. Right. So here's the results. So this is so confidence level limit, a current limit on the branching fraction of the vector lepton to d plus mu. So actually, we have still one more parameter of the branching fraction of the vector lepton to d prime to mu. And so we put the upper bound of this branching fraction depending on the masses of the vector lepton and the d prime. So the left panel shows a limit in the case of the singlet vector lepton, and we see that if the branching fraction is 1, then the limit is about 1 TeV. but the limit is weaker for the smaller branching fractions. And for instance, if the branching fraction is 0.3, there's no limits. But this is just a singlet vector lepton, but we still have the very strong constraint of about 1 TeV at LHC from the current data. And also this is a case for the doublet vector lepton, and the limit is about 1.3 TeV if the branching fraction is 1. And of course, the limit is weaker for the smaller branching fractions. And I note that the limit is weaker from the 5 lepton signal regions because of the excess, and also the model predicts in many cases only for muons. So the accept efficiency factor is much larger for the other 4 lepton signal regions in most parameter space. So basically these 4 lepton signal regions give the strong constraints on our model. And here is a future limit at the high limit C. And I only show the case of doublet vector lepton, and the links coming from the tight signal region is requiring only 4 muons. And now we see that the bound can be about the 1.6 dB or so. So yeah, actually this limit can be very, very strong. And this white line is the upper bound for the discovery potential. So that actually we can find the vector lepton up to 1.5 dB if the branching fraction is 1. And we have some sensitivities even if the branching fraction is about 0.25. So this is a very nice result to have the very strong constraint in the future experiments. And also, but so this is a very rough cut and not so optimized for our case. So we can suggest a more good way to constrain the model. So because we have the D prime, which indicates a dimuon system, it would be nice to require the cut for the opposite sign invariant mass for the dilepton or dimuon system. So for instance, so here we require the very rough cut about the opposite sign invariant mass should be close to 500 GB with a width of 100 GB for the first candidate pair, and for the second pair, it's just a 250 GV. So even if this weak cuts, and sorry, this is a very rough estimation, is assuming that only there are 10 backgrounds, but the limit can be tightened for this region where the D prime mass is about 500 GV. So I think that this is a very powerful way to improve the sensitivity of this kind of signal by requiring this invariant mass requirements. And also, of course, we can change this value to some different values, and we can get more stronger bands in all the other parameter space, this varying D prime. And also, I note that I think this is a very a conservative limit, because we only have the muons. If we require only the muons, then background is reduced, and this is very strong cut for the standard background. So I think this is a very conservative limit. So I think we can get stronger bands. Okay, so finally, let me discuss about. Okay, do you have any questions?
May I ask? Sorry, the final state is only leptons.
Yes.
So what did you do for PCR8 and Delphis 3? Only lepton, but you did some electromagnetic shower or something?
Yeah, we so I don't understand what the intention of your question, but
yeah, because the final state is only leptons.
Yes.
So that we don't have to the hadronic showers. We don't.
Yeah, but for so this is some standard way to follow the but so that I for just in case I apply the PCI for showering and hadronization, but actually I think this doesn't do nothing. This do nothing.
I see. How about electromagnetic shower?
Yeah, of course, showering is also done by PCI, and it it's counted by counted by the calorimeter.
But almost.
But yeah, only the relevant one is how the leptons are dealt in this this process. So actually, it's not so important here.
Oh, thank you very much.
Because we don't have any quarks.
Yeah, thank you.
I have a question on the decay of the vector-like lepton. So in the case of doublet vector-like lepton, it also decays into standard model G boson.
Yeah, that's possible. Yeah.
Muon or W boson plus neutrino. So
yeah.
that possibility also exists, right?
Yeah. So actually, that's included in this branching fraction. So if there is such a decay mode exists, then this branching fraction reduces. So this is the reason why I put the upper bound on this one. But in many cases, actually, this branching fraction is close to 1. Maybe I can show you some value here. No, sorry. In this case, sorry. Yeah. You see that in this case, actually, this is a 1. And I also calculate the decays to Higgs and the WG and everything. But in this case, this is very negligible for the vector lepton. Yeah. So because the strong coupling to the vector lepton to the muon, so large mixing is required. So the coupling to the D prime is usually the largest one. But it's possible that it can partially decay to the some boson.
And also the neutral vector-like lepton decays into G prime.
Yeah, right.
So the missing energy signal in that case.
Yeah, or in this case, this can be neutrino. And so, but even if with both D prime decay to muons, we have a 5 muons in the final state. Yeah, something like that. Sorry. If the consider the production of the charged vector lepton and the neutral vector lepton from W boson, then we still have the 5 muons. Yeah.
I see.
And these are calculated. These are assuming this branching fraction of the D prime. Okay, so let me discuss about the explanation, whether we can explain the excess in the more than 5 lepton signal regions. And the non-trivial point here is that we should explain the null excess in the other signal regions with requiring only the 4 muons. And the difference between these two signal, among these signal regions, whether we require the M effective cut or not. So in this 5 lepton signal regions, there's no M effective cut. So the effective distribution may be important whether we can explain this null excess in these signal regions. So here's the effective distribution of the new physics contribution when in a case that the vector lepton mass is at 400 GeV or 1 TeV. So if the vector lepton mass is about 400 GeV, it's distributed around 800 GeV, which is about twice the mass of the vector lepton mass. But in the case of the heavier vector lepton 1 TeV, then the limit it's distributed around 2 TeV or slightly less. So actually, the heavier vector lepton mass easily pass the cut. Okay, so to explain the null excess in these 4 lepton signal regions, actually the lighter vector lepton mass may be preferred. So next, actually we find good points that can explain the excess, and here is the emissivity distribution. And so the yellow is a standard background, and the black dots are the data. So now we see that the large, not large, but some discrepancy between the data and the sum of the backgrounds. And this can be explained in our new physics contribution from vector lepton production. And here is the new physics data. So it looks like the experimental excess explained our new physics contribution. And so in this case, we consider the vector lepton mass of the 400 GeV, and the branching fraction to Z prime to vector lepton is about 2.25. So, and we checked that the number of signal events are less than the current limit in this other signal region at this point. So this looks nice. at some point we can explain the excess. But I should note that our model only predicts the muons. All 5 leptons or 6 leptons are muons. However, the experiment also counts electrons. They don't distinguish whether it's electron or muons. So if the experimental results have the excess also contains the electrons, actually our model cannot explain that. So, but we don't know that whether this is really true or not, whether there is an electron or not. But anyway, so in principle, we can explain this excess by our model. Okay, so let me summarize so in a model with vector family and the UN prime, we can explain the muon G-2 and the BATS muon anomaly simultaneously. And in this kind of model, there's an interesting possibility to have the more than 4 muon signals. And the current limit is more than 1 TeV. The branching fraction to the Z prime is about 1. But the future sensitivity can be as large as 1.2 TeV, even for the singlet vector lepton case. And we show that the excess can be explained if the vector lepton mass and the Z prime mass is about 400 GeV. And the important, interesting feature is that in high limit LHC, this point can be discovered by the full data of the high limit LHC. So we are looking forward to see the future result of the future experiments. Okay, so that's all I have today. So thank you for your attention. I'm done.
So thank you for nice talk.
Thank you.
Is there any question or comment?
So can I ask a question on the 5 lepton excess? You said that there is no cut on the M effective in that case, or?
No, they don't require.
Let me see. No, yeah, there is no cut in the M effective. And then you showed the missing ET distribution in your model. And then you said there's some excess in the data.
Yeah.
It's excess is 5 lepton. You said the 5 lepton. There's excess. Is the excess due to the missing energy, or what is the origin of the excess in the 5 lepton signals? What do you mean by the excess in the 5 lepton signals? So do you require that the leptons to be 5, number of leptons to be 5, and then you have excess in the missing ET distribution? I mean, from the data. How can I understand?
So in this case, I think so that the missing ET is just coming from some imbalance of the lepton, because sometimes some leptons are missed because of the, for instance, some wrong direction, too large eta or something like this, or some because you have some this limited resolution for the PT, so we have some imbalance. And so the missing ET is actually not so very significant, I mean, predicted feature of our signal. But just I think it's good to show, because actually I found that this distribution data from the experimental paper, and I wanted to show that how we can see, how we can explain this discrepancy. So so this is just a similar distribution as the sum of their background, because these are just coming from the imbalance.
I see. Okay.
In many cases, yeah.
So I see. In principle, okay. So those particles, you have a pair production of vector-like leptons, and in principle, if there is no invisible particles, the momentum must be balanced. But you might have missed some of the leptons, and then you don't see it, only 5 leptons, and then look for the missing ET due to the missed lepton somehow. And
I think so. But
maybe
because
okay,
missing ET is not so required to be large. So the largest contribution is of course coming from this almost 0 missing ET. So I think so. This is consistent to be.
So as the number of events is a small. I see small. I see the events with the small missing ET is the largest, but still there's some excess due to the excess. I mean, in the 5 lepton signals, you have excess in any case. So correspondingly, you have excess also missing ET distribution being proportional to the number of events of the 5 leptons. Maybe just the overall kind of over excess, probably, right?
Yeah, so we had that,
Yeah.
Particularly in these 2 beams.
So
actually, there's no event at here in this beam, but at these two small missing ET beams, we have some excess.
Okay.
Also, this is of course not so significant.
See. Okay.
Sorry, how was the detector cut for lower missing ET, for example? So missing ET, so missing ET also has some cut, detector cut, I suppose.
No, I don't think so. They don't require any requirement for the missing ET. Actually, this also studies the missing ET in some cases. So they also study more signal regions, but I only show the some most relevant ones. And at least in this signal region, they don't consider any missing ET cut. Of course, this is quantitative and effective, but this is small, at least for this signal region.
I see. So that the missing ET, even if lower than the 5 GeV can be detected?
Yeah, I think so, because the trigger is given by some lepton should be detected. So any requirement for the missing ET in this kind of analysis.
Because the M effective is observable.
Yeah.
So I see. So that the PT already 5 GeV should be more than 5 GeV, so missing ET can be 0.
Yeah, or I don't remember exactly, but they require, so the trigger requirement is more complicated. So for instance, it should have 20 or 30 GeV lepton, 1 lepton, or some 2 leptons with larger than 20 GeV or something like this. But this is not a strong constraint, of course, for our signal, because we expect that these are 1 TeV, and their decay products will have the very large decay, like 50 GeV, or is maybe natural. So yeah, it's not so strong constraint for the signal, of course.
I see. And that missing ET distribution, no cutoff. I see.
Yeah, there's no cut. Yeah, these are all counted in the signal region.
Thank you very much.
Yeah, I think they show this missing ET because they are looking for some alpha developing supersymmetry, and in these cases, in general, we have some neutrinos in final state. But it looks like the missing ET, their missing ET is the most favored in the signal region. So I think there's no evidence of such a large missing ET signals.
Thank you very much.
I have a question. So for instance, I think that there's a strong bound on this visible decays. I mean the G prime muon and G prime decaying into 2 muon anti-muon pair. So you have many leptons in the final states. Suppose the G prime decays into something else, and then, for instance, decays into dark matter, invisibly decays, then it seems that you have only 2 muons plus missing ET in the final state. I mean, in that case, is it similar to dimuon searches for G prime? Sorry, it's not G prime, but so it's a dimuon search in any case. It's not resonance, but you have a dimuon plus missing ET in the final states.
Sorry, which production are you considering?
So suppose the vector-like lepton.
Vector-like lepton?
I'm talking about vector-like leptons, and I want to modify the decay, the branching ratio for G prime. The G prime
so
decays invisibly into some dark matter, for instance.
So I also study, so you mean that Z prime may decay to neutrino or some other invisible particle, right?
Yes, yeah.
So in that case,
algebra integration.
So at least this is partially included in our analysis because we are considering different medicated neutrinos. But of course, but with fixed decay, this decay width, so branching fraction of 1/3. Yeah. So if there's such some invisible particle, then yeah, this can be much smaller. Then in that case, actually, the signal looks like more like just a lepton search in SUJI.
I see.
Because these are just a missing particle, and these are two muons, so just a 2 lepton plus missing ET. Yes. So actually, I also in the analysis we also studied the 2 lepton plus missing ET search, but that limit is much weaker compared with this 4 lepton search.
I see.
Yeah, because of the large background in 2 lepton plus missing ET.
I see.
Yeah, that's possible, and yeah, there can be such a model, I think.
So do you remember the current limit on lepton-like particle with invisible?
Yeah, for the vectorlike leptons?
Vector-like lepton might be severe. Maybe cross-section is larger than.
Yeah. So it can be much larger. And when I studied this in 3 or 4 years ago, the limit was about 900 GBU or so. If the branching fraction to such a decay mode.
Lepton, yes.
So that
stau, right? Stop or sparton, you have a similar invisible decays. For lepton, the cross section is smaller, so there is no gluon. So I guess the cross section is smaller than the colored particles, and is 900 GB for lepton.
No, vector-like lepton. For lepton, the limit is weaker.
For vector-like lepton. It's very severe.
But yeah, can be strong because of the larger production of section for fermions. And yeah, we can still get some strong band.
I see.
Is there any other question or comment?
There should be some question from the students. I think that I want to encourage students to ask any question, simple question. Okay. Normally, students are not asking a question, only only me or some postdoc. So, do you have any question from some graduate students? You're satisfied. Okay, so but I think that is very nice talk, and yeah,
thank you.
I think that we can discuss later. Yeah, we can keep in touch, and
yeah, sure.
Junichiro, I have a naive. Just a curiosity. I'm not so familiar with the detailed analysis, but so for the setup, you have force family, which is vector-like. So is it possible to embed such a setup to more fundamental theory, like GATT or extra dimension or?
Yeah, so actually this charge assignment is somewhat motivated from the ground unification. So actually we found that this sign, this sign is actually flipped for some particles. So actually this is for the left doublet, SUTL doublet sector for the minus, and for the singlet sector, these are plus. So we also studied the case that these are all +1, which can be directly embedded into SO10 unification or SU5. But this case actually not favored to explain the anomaly. So because this coupling is forbidden by muon prime symmetry. then we cannot get the muon G minus 2. So that's a good point. And then, so actually this is motivated by the patch-salam unification instead of SO10. So this can be directly embedded into the patch-salam. So I mean, just not a U1 prime, but only the standard sector can be directly embedded into the patch-salam unification, where this doublet, ST doublets are unified into one multiplet, and this singlet unified into one multiplet.
I see. And in that case, you have I don't know, additional contents because there are fields.
Yeah, so in the vector fields and also some scalar vector sector should be extended to break the symmetry.
But you mentioned this kind of charge assignment can be realized such a setup.
Yeah, but just without conflicting with the symmetry.
I see. Okay.
And it's the orthogonal. This U1 prime is orthogonal to that symmetry.
Okay, thank you. So maybe it's time. So if there is no further question or comment, so let's thank Junichiro. Thank you.